Welcome to IT Fundamentals. We are in Scrap Mechanic, and today I'm going to go into numbering systems. Now, usually this means decimal, hexadecimal, and binary, and that's what we're going into. I'm not going to mess with pesky octal. Nobody cares. So, looking at this scale of numbers behind me with the duck on the elevator, well, let me get up and look at it with something that doesn't highlight things. All right. So we look at it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In decimal, we have 10 digits, just like 10 fingers on our hands. And so we count starting from 0, which of course isn't a count, means we have nothing. And we start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. But when we get to 9, we run out of digits. We don't have any more digits. So we have to go into the tens place, or 10 to the first power. And then, of course, we continue counting. When we get to 99, we have to go over to the next place, which is the hundreds, and so on and so forth. And that's decimal. We know it. We learned it in kindergarten. We may not have understood it to that level, but that is decimal. Now, enter binary. Where you only have two digits, a 0 and a 1. And then once you've done that, you've run out of digits, so you have to move over to the next place, which means you go to 1, 0. Okay, and then you can keep on counting. And then when you run out of digits again, you go to the next place, and then you just kind of continue once more. And then you just keep counting up and up. So we can represent every number because since we run out of digits at after 1, the next place is 2, or 2 to the first power. And then when we run out of digits again, after 3, and then we have to go to the next place, which is the fourth place. And each place, so we get 5, 6, 7, and then when we run out of digits again, or bits again, we go to the eighth place. And then there's a 16 and a 32 and a 64. Each time it goes up by 2. Every time we add a bit, we go up by 2. So 2 to the first, 2 to the second, 2 to the third. So it's referred to as the base system. So we base 2 because when we figure out the value of each place, it's 2 to whichever place it is. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. But that's the higher math in it. The one thing that you want to get into with as far as IT goes is if I take a look at 1 and I take a look at 4, that would be 5. I can come up with any number between 0 and 15 with this. So 1 and 4 is 5. And it escalates this piston up to 5. So let's look at this in Scrap Mechanic. What I've done here is I have this stack of 4 pistons. You know what, let me bring it back down to 0. Is I have this stack of 4 pistons. This one set to go up by 1. This one goes up by 2. This one goes up by 4. This one goes up by 8. And I couldn't continue on for that because pistons can only go up to 15. Gee, imagine why the developers chose the range from 1 to 15 for the pistons. Well, it's because they only used 4 bits, or I would assume. I didn't look at the code. I would assume they only used 4 bits to determine the state of the piston. So when I hit the 1 and I tell it to execute, it extends the 1 piston. And the elevator, the duct, goes to 1. If I extend the 8, it'll extend the 8 piston, and the 8 piston plus the 1 piston ends up being 9. And that's all binary is, just a way to express a number, because you can express a number in that manner. Anything between 1 and, well, 15 with 4 bits. If I only have 2 bits, then the highest I can go is 3. Now, more practical use of this idea. Ever seen a 3-way light bulb? 3-way light bulb has 2 filaments in it. One that's a little dimmer than the other. So I've got 2 lights. That's 1 and a 2. And this one has a brightness of 4 and this one has a brightness of 8. So I can have a variable brightness of anything between 0 being off, 1 and 15. But here it is with 3. And you can kind of see how much light is there. But if I take away the 2 lamp, it's not even really recognizable. But I could also turn this on. So I get 4 choices. So with 2 bits, I get 4 choices. So with 1 bit, I get 2 choices, a 0 and a 1. 2 bits, I get 4 choices. With 3 bits, I get 8 choices. With 4 bits, I get 16 choices. So which leads me kind of to this, and where we come into play with computers. And while the numbering system and understanding binary to decimal and decimal to binary is kind of there, say for instance I wanted to convert decimal to binary, say the number 6. Well, I know 4 plus 2 is 6, but just to do it the proper way, 8, you can't add anything to 8 to get 6, so that's going to be 0. 4 is less than 6. So we turn on 4. So we turn on 4. So we know that 4 plus something equals 6. So if we subtract 4 from 6, we get 2. So we know that 4 plus 2 is 6. Very simple math. Now, of course, if I push this, it loads it into that. Why is it flickering? I don't know. Over here, I've got 2 address registers. Now, these address registers determine when I put in a number like 8 plus 4 plus 2, so that'd be 12. So when I put in a 12 here, it will load into a different register. Now, right now, I have it 1, 1 in the address, which means 2 plus 1 is 3, so it loads into that top register. And for some reason doesn't flicker. Okay. So each one of these gives me a different register. So if I put a 0 in, well, that was a 4. And if I put 0 in, okay, it loads into the bottom register. So with 2 items, we have 4 choices. Now, this kind of leads us to another thing about computers. If you ever noticed, every time they talk about units and specifications, you have 1 gig, you have 2 gig, you have 4 gig, you have 16 gig. Why not 3? Why not 12? Well, those are certainly possibilities, but it's usually because of this. When we talk about the number of bits in a bus and how many choices we have, if you take 2 to the 32nd power, you get a little over 4 billion. And that equates to the 4 billion addresses, or basically 4 gigs of memory. If we take 2 to the 10th power, you get 10,024, which is why in some cases a kilobyte is 1024 bits, because they're looking at a binary kilobit. And incidentally, a lot of manufacturers will utilize the binary kilobit just to make the number look bigger. On the other hand, depending on the operating system, whether they go in binary kilobits or decimal kilobits, then you'll either end up with 1,000 bytes or 1,024. And at that level, it's not that much. But when you get into megabits and gigabits, you're dealing with multiples of 1024 as opposed to multiples of 1,000. And that is why it seems like a big marketing sham. But really, the numbers in binary and your kilobits and megabits and gigabits were based on a 10-bit bus, a 1000-bit 10-bit bus, a 20-bit bus, a 30-bit bus. With 10 bits, we can address 10,024. With 20 bits, we can, well, 10,024 squared, which is what we go into a gigabit today, or megabit, not gigabit. Gigabit would be to the 30th power, and then 32 would be basically 2 times 10 to the 30th, but 4 times 10 to the 30th, which would be 4 gigabits, which is the limitation we have on 32-bit addressing. And that's where that whole addressing, if I have 2 bits of an address, if I have 4 bits of an address, and it was one of the important things about the size of the addressing bus, which is where we get into 64 versus 32. 32 bits at a time, 64 bits at a time. 64 bits at a time can deal with more information or larger numbers than 32 bits. All right, so moving on. The third numbering system is hexadecimal. So I'm going to come back to the bottom of this one. And you'll notice that the labels on this are all one character. Now, 4 bits is a number between 0 and 15. So if I turn all of these on, or better yet, just 8 and 2, so 8 plus 2 is 10. Now, if I wanted to represent that as a single digit, of course I could represent it as 1, 0, but that's 10. So we have to represent it as a single character, not 2 characters. So the choice was made, go into the alphabet. So 10 becomes A. 11 becomes B. Let's see, 12 becomes C. 13, D. 14 would be E. And 15 would be F. There you go. We have a way to represent it. And the idea was to represent 4 bits at a time with just one character. And this is really useful in that you don't have, if you want to represent binary data, but you don't want to just fill out a bunch of 1s and 0s, you just take it 4 bits at a time and code it in hexadecimal. Yeah, and notice at F, this is really bright because all of the lights are on. And while we're here, we have a printer. Okay, it's an old printer. This is what I worked on a long time ago, one of the many printers I worked on. But one of the ways that I had to troubleshoot it is when it gave an error, it sent back to the system that it was working with, I want to say 64, it might have been 128-bit error code. And it was written in hexadecimal. And in order to figure out and interpret the error code, I had to take each hexadecimal digit and break it down into its binary, which was very easy. You could just, after a little bit of memorization, you could easily just memorize, okay, D is 1101 and so on. That you could just go ahead and just look at the numbers. And eventually, through practice, I knew which number digit to look at for certain symptoms I suspected. But that's another IT fundamental. That's troubleshooting. So I would use that, and I would break down, and it would tell me exactly what the printer was doing when it failed. So I knew where to go in that printer and look for the problem. In many cases, we see hexadecimal in dumps or readouts, especially if we're just looking at what's called binary data. Sometimes it's used to represent binary data. Now, you can do math with it. You can add it, you can subtract it, you can do lots of other things with it. But really, what we use it for is to represent 4 bits in one character so that we can have something like a MAC address or IPv6 address or memory locations that we can look at usually, and all of the things I just mentioned are addresses. So addressing, we're not interested in adding or subtracting. Now we might go up by X number of addresses, like go up by 4 addresses or go back by 4 addresses, and in that case, yes, you're doing math, but actually that's relatively easy. But we use hexadecimal digits just so we can make 4 digits into 1 character at a time. And that's really it. Just to represent the binary data. And so that is our short look at numbering systems. Decimal, yeah, we know that one. Binary, fairly simple. Add them together, add together the values of the bits, and through it we can represent each one. And even on a practical level, we can even break it down by looking at the different values. And something as goofy as scrap mechanic here, I can make a set of 4 pistons that I can select which height I can go to through 4 inputs. At least up to 15. And then hexadecimal is merely just a way of looking at it 4 bits at a time. By the way, 4 bits is a nibble. 2 nibbles make a byte. 8 bits. And then past that it gets a little shaky, because then you get into 16-bit words and 32-bit words. When you have multiples of bytes, then they start going into words. But that's the IT fundamentals of numbering systems. Hope you learned something. Have a good day.